Well, good day and good morning. My name is Gregg. It's great to be here. This is my first Meet BSD. In fact, I think it's my first BSD conference entirely, so yesterday was really fun, and I've learned a lot. So this morning I'm going to do a quick talk on performance analysis and observability of BSD. And I've come up with a nice diagram to show generally where the tools fit together. I've been updating it. I've now got IPMI tool on it, which is nice. I know I probably need to adjust some of these layers just to make it meet. I'm currently reading the design and implementation of FreeBSD 2nd edition, which is fantastic. And so hopefully I'll improve this diagram and it will get more detailed. I work at Netflix. We do FreeBSD for content delivery. We've got some of the engineers in the room, and that's the Open Connect appliances. I know a lot of us here are familiar with what Netflix is doing, and we're hitting approximately 33% of the US internet traffic at night going through FreeBSD, which is pretty awesome. We currently have Amazon EC2 Linux for cloud. We have a Linux cloud for doing the interfaces, the front end to Netflix. But as soon as you start playing things, that's all coming from FreeBSD. I would like to investigate doing the front end from FreeBSD since Amazon has an AMI for PV-HVM support, which is going to be really important. But I'll need to benchmark that and see how it goes. But that would be pretty interesting. My name is Gregg. I do performance analysis at Netflix, and recently I've been playing with pmcstat and doing new flame graphs with it, which is really exciting, and also developing DTrace tools for the OCAs. So I'm going to go through 5 facets of performance analysis in 45 minutes. 5 important topics just to cover: observability tools, methodologies, benchmarking, tracing, and counters. So observability tools, and that's why this diagram can be helpful. So think about how you measure each of these components. Often with, and I've decorated it with FreeBSD, but I understand FreeBSD is what I have most experience with. I understand this probably is fine for OpenBSD and other BSDs as well. A big problem with performance observability is there are a lot of tools and there are a lot of components, and it's easy to miss things. And so having diagrams like this helps because you can use it as a checklist, make sure you've checked everything. Quite often, a lot of the very large performance wins you find are because you simply ran a tool and you saw that the workload to this component was pretty crazy, but no one had looked at it before. It had been overlooked. So just getting the basic observability of all the components is pretty important. Observability tools themselves are generally safe to use. It depends on their resource overhead, and the BSDs currently have awesome observability tools. So this is a premier observability platform. And for me, when I work on Linux and then I work on FreeBSD, which is part of my job, on Linux, things can be tough, and you get the job done, but it requires a lot of expertise, a lot of working with all the different traces. And then I go into FreeBSD, and then I can just fly around and work at 100 miles an hour. It's quite different. And that's, of course, performance observability is important to Netflix. It's small wins can end up being big savings, so we pay attention to this quite closely. Apart from utility, these tools that FreeBSD have are also a competitive advantage, which should be pretty obvious. And that's about solving performance issues instead of wearing losses. So a misconception when comparing operating systems is to do just the out-of-the-box performance of, is my micro benchmark 5% faster than Linux or 5% faster than something else? What I care more about is, can I identify and solve the really dumb problems that we generally have? And those are the ones that give you the 2x wins and the 5x wins. Because as soon as you have the first 5x win, because you happen to have DTrace or you happen to have pmcstat, then the 5% don't, it's going to put them in a different perspective. So having really good observability tools trumps just out the few percentages you get out of the box. Especially in an environment like Netflix, in the cloud, we're changing the application code every week, almost every day. And so there are going to be these large low-hanging fruit problems, and you just need good observability tools to identify and fix them. The first section I wanted to talk about observability tools, but these are pretty obvious, so I'll just go through them briefly. I've picked a few examples. Uptime is where a lot of people start. That's one way to print out the load averages. At least on FreeBSD, uptime is the way Unix intended. It is the CPU demand, runnable plus running threads. I always get confused when I'm on Linux because it includes the NR uninterruptible as well. These numbers are not 1, 5, and 15-minute averages. They're exponentially damped. So 1, 5, and 15-minute are constants used in the equation. So they kind of roughly resemble that. It's really cool, actually, because this is a historic trend. It comes from 10x. This is a way of doing, so you can see if things are changing over time just using numbers, just using text. Of course, if you asked anyone to implement this today, they're going to go and use D3 and give you a line graph. But back in the 70s, you don't have visual displays as easy to access. So it works just fine. And so I can see if my load is getting higher more recently or going down. So I'd like to actually use these, like the triplet of loaded exponentially damped averages in other areas as well, because it does kind of work. However, don't spend more than 5 seconds studying these. This is just like checking the pulse rate of a patient. You should then go and use all the other tools. And I've generally said if the load is greater than the number of CPUs you have, that probably means you've got CPU saturation. I'm sure we all run top minus capital P to do the per processor statistics so that I can look at the balance of what the CPUs are doing, and if I need to tweak that or tune that or change the application to make use of what's available. Top does do the exponentially damped averages just for the CPU, which is the W CPU column, and you can toggle that and go to just the raw metric. vmstat is another a very common tool, just to mention as part of the basic observability set. Virtual memory statistics and more came from BSD. Standard usage, interval and count. First output line shows the summary since boot. And it's our high-level system summary. And so I've been highlighting some of the columns that my eyes go over. So what's my run queue look like? So how many threads? This is very, very, very coarse metric, but generally if that's non-zero, then it means I might have some level of CPU saturation. Memory statistics, and then system calls, context switches, and then general CPU averages or breakdowns. Great just to get an idea of what the system is doing. Iostat, I actually really like the design of iostat, and so on FreeBSD you've got the workload analysis columns and then the resulting performance columns. And so with iostat I can do a whole bunch of different methodologies just based on these statistics. So workload analysis, this is what's being applied to the system, the target. So reads per second writes in kilobytes and the throughput. And then you've got the resulting performance, so queue lengths and service times and a % busy or form of utilization. And that's great because I can do a workload analysis. That's where you just want to know what is being applied to different components, because often big performance wins can be found just by turning the light on and seeing that the workload applied is actually pretty dumb. So that serves this purpose. And I can also characterize that for other analysis. And then resulting performance serves other methodologies as well. So I can use those numbers if I want to do modeling with queuing theory, latency analysis, and so on. Again, it's another high-level statistic, so you do kind of want to break this down into latency distributions so that I'm not just looking at the average. I want to know what my, I don't want to say 99th percentile because I often actually want to look at deciles, I want to look at a histogram. When you're accessing disks have inbuilt caches, and so you'll have a multimodal distribution of cache hits and cache misses. So generally, I do want to look at either a density plot or a histogram of disk performance, or a heat map. I wish it had -e for an error column. Then I could do my use method just on iostat. So if someone wants to add that, that would be great. And then there's systat on FreeBSD. I don't know if people pronounce this systat. It has lots of cool things. So ifstat, and generally on systems, I'm sure a lot of us alias this, so it's easier to type. So I can go and bring up my network interface throughput and see what's going. And it's also got modes for TCP statistics, iostat statistics with a histogram, so you can look at balance at the drive level. vmstat, which gives you lots of breakdowns, including interrupts, name cache statistics. And then the last one is DTrace. DTrace allows us to trace any software, so whether it's user level or kernel, and then I can compose custom instrumentation to answer basically any arbitrary question. It's really a catch-all, and I don't start with DTrace, I start with everything else, including pmcstat, and then if I can't answer it, then it might be a job for DTrace, where I can come up with some custom instrumentation to fill in the gaps. But another question I want to raise is, having drawn this diagram and just briefly mention some of the tools, and there's only going to be more tools over time, so we keep adding tools. It starts to become laborious just to run all the tools. And we have to question, it starts to become a problem for people who are new to performance analysis, just the process of having to learn everything, knowing where to start. That can be solved with methodologies. And that's something I've been studying a lot. Methodologies, we have many awesome tools in BSD, but these are only awesome if you actually use them. The real problem becomes how to use them. So methodologies can guide usage. I really, this is something that occurred to me when developing and teaching classes in systems performance analysis, where I'd pose problems for my students to solve. And I would cover how to use the tools. This is how you use all the tools. This is what it all means. Here's the background of how the kernel works. And yet, people weren't solving the problems, because the real challenge was where do I start? And what's the mental process of going from, I have an issue, where do I begin? What's step 2, step 3, step 4, down to root cause? And I've taught many classes and developed many classes and realized that something that performance engineers like myself need to do is write down the methodologies that we're using. As a junior system administrator, this was always the black art that the performance experts knew, that you wish they would write down, and it's something that I've been trying to write down to help people pick up. So, just to help you understand methodologies, I've also come up with the idea of anti-methodologies. So this is the lack of a deliberate methodology. So the streetlight anti-method, which is named after a parable about a drunk who has lost his keys, and he's searching for them under a streetlight. And a policeman asks the drunk, "Did you lose your keys under the streetlight?" And the drunk says, "No, but this is where the light is best." And I kind of see this when people are doing performance analysis. They're running top. Why are you running top? Like, there's lots of other tools on BSD you can use that are pretty cool, but top is what they're familiar with, and they're just looking for obvious issues. Another anti-methodology is, you can either call it the drunk man anti-method or the whack-a-mole anti-method, and that's where people just change things until the problem goes away. After naming it, I had a performance issue at work where I come to work the next day and my colleagues say, "Oh yeah, we fixed that problem, Brendan. We used the drunk man anti-method." And it was actually really useful for them to confess to this so clearly, because it's like, okay, now I know why these weird tunables exist, because you just randomly picked it and solved the problem. Then there's actual methodologies, which is how you solve issues. So the use method, it's something I've come up with. It's just one methodology. It's useful early in a performance investigation, and you might spend 5 minutes on it. Ideally, you have a GUI that does it for you, that gives you the right metrics. And it's pretty simple. For every resource, hardware and software, you want to check 3 metrics: utilization, saturation, and errors. And that's it. A big problem with performance analysis is we have lots of metrics, and people keep adding metrics. And so this becomes part of the laborious task that it is to wade through all the metrics. What's nice about the use method, and I've come up with a picture for it, is you only have a finite number of hardware components, right? So there's what, a dozen? Now you only need 3 metrics for each type of component. So now you have, what, 30 metrics. That's much better than if you start with a system and run netstat minus s and start reading through everything, and you actually have maybe 100 or 200 metrics. Now you've got just 30 metrics, which can really identify bottlenecks and errors early on in an investigation. The other nice thing about the use method is, if you start with the system and you think, well, I'm just going to read all the metrics, surely the performance problem is in one of these metrics. there's always areas of the system which don't have metrics because the engineer hasn't added them yet. So it's the assumption that the metrics will give you complete coverage of the kernel, and that's not the case. There can be gaps. When you start with methodologies that reverse it and pose the questions first, then it forces you to look into areas that you may have otherwise missed if you're just using the tools and just using the metrics. So that's another reason why I like these methodologies. It gives you better coverage. For the use method, I have come up with a FreeBSD performance checklist, which I have online. It's very long, and you can print it out and so it looks like this. You can print it out, stick it on the wall, or you can improve it actually, because I'm sure I've probably messed something up. But this just gives you an idea of how you do this methodology. I've got my components, and then I've just got 3 metrics for each component. And then I want to know, how do I measure that? And of course, we're going to go down into interconnects and controllers, and they're all part of the system. They're all part of the data path. So you do want to understand their utilization, their saturation, and their errors as well. I've also come up with a little list of software resources. This sometimes works, and it's just a methodology that helps you identify metrics. So you can come up with some metrics for software resources like kernel mutexes, user mutexes, and so on. Like, for example, with a mutex lock, does utilization make sense as a metric? Well, you could say the lock held time is a utilization form of metric. What about saturation? Well, that's going to be lock contention. What about errors? Are there any error statistics that make sense for them? So this methodology doesn't solve all issues, and it's not that important. It's just one methodology you might use to help identify some metrics that are useful. And I did mention a couple of other ones as well. The 5 whys methodology, which is pretty simple. I can put it in one bullet point. When you're looking at the performance of the system, ask why. Oh, the performance of the system is bad because the CPUs are hot. Why? Why are the CPUs hot? Well, the CPUs are hot because it's in kernel space. So I looked at vmstat and I saw it was mostly system. Okay, why? Why is it in system time? Okay, well, it's in these drivers. Why is it in these drivers? And so just using that methodology can help you pose the questions, because it's coming up with the questions that's often harder, the questions that are actually relevant. Some other ones I mentioned briefly: workload characterization, drill down analysis, event tracing, baseline statistics. It's this whole area of performance analysis that I'm trying to document, and I think is quite effective in helping people pick it up. Benchmarking is another topic. And I could give just it's a really important topic that I wanted to include today, just as part of 5 relevant topics for performance analysis. I could give a whole talk on benchmarking. It would be really depressing. I'd have to give everyone booze or something beforehand, or I don't know. We can arrange that. So the problem with benchmarking is basically 100% of benchmarks are wrong. And it's kind of counterintuitive. So I'm often sent benchmarks where people think, this professional firm, whose job it is to benchmark, has published a paper on the performance of this product. Surely it's correct. And I've spent a long time doing benchmark analysis as a job and refuting these benchmarks. And I always want to say 100% of benchmarks are wrong, because I can almost refute every single one of them. But people wouldn't believe that, so I put a tilde there. Almost 100% of benchmarks are right. It's extremely error prone. A big problem we have in the industry is the energy needed to refute benchmarks is much higher than it takes to create them. So you can just run Unix bench and come up with a bunch of numbers and then publish it and make all these bad conclusions about OS performance. And it takes a long time just to refute that. It can take a week just to explain what a micro benchmark has really done and why that matters. I started writing a series of blog posts on Unix bench. Speaking of being depressing, I only got as far as how the thing was compiled, and that was it. Because I mean, the way it's compiled is you need to know about that, because it can vary to the point where you're not actually testing the resulting performance of the system. Unix bench is testing its own makefiles. So how its makefiles were written from one system, for like if Linux optimize, if other operating systems maybe not optimize so much, It's like, wait a minute, but you're testing the makefile, you're not testing the target. So yeah, this happens all the time. Benchmarking, apart from observational analysis, benchmarking, like while it's really depressing that it is so error prone, it is useful. And I think of it as another hand. So I do observability to study systems, and then benchmarking, which is a different way of getting metrics out of systems to understand how they work. It's just really error prone. Like testing the wrong target. A common one is I wanted to test disk I/O, but I didn't check what the benchmark did. It actually just hit out of the file system cache. And so, wow, my disks are doing 10 gigabytes per second. I don't think your disks are doing 10 gigabytes a second. I think you hit out of the file system cache. Second problem, choosing the wrong target. Testing disk instead of the file system cache. So people want to test disk performance, especially, it's something that drives me nuts, especially on the cloud. Why are you testing disk performance? Do you have an application that talks directly to the disks that always does synchronous I/O or bypasses the file system cache? Applications often don't. I mean, if you do, that's great, and that's why you're testing disk performance. But a lot of the times, people are testing disk performance because it's not a terrible methodology. It's the notion that that's going to be the bounding resource of my system, so I may as well make sure that's the fastest one. And so then the system will be okay. But in reality, your applications, most applications are going to be bouncing out of the file system cache. And so doing a file system cache-based benchmark will give you much more accurate or numbers that resemble real-world usage much better. Sometimes there's bugs, and very often benchmarks are misleading. FreeBSD has ministat you can use as well, actually, to do statistical analysis. So you can take benchmarks and get some statistical faith in whether they have too much variance or whether they seem accurate. Benchmark examples. Some bad benchmarks include get pit in a tight loop or context switch tuning, which we had mentioned yesterday. Micro benchmarks, so just if you're new to the terms, micro benchmarks are where we're testing, say, file system, maximum cache read operations per second. Macro application benchmarks are where we're simulating an application. They're both tricky, error prone. They're both useful when you do them correctly, but you have to be very careful. I want to introduce the benchmark paradox. Benchmarking is often used for product evaluation. So at Netflix, we do have Linux on the cloud, but if I want to try out the FreeBSD AMIs, which do PVHVM, which sounds pretty good, it is going to come down to performance. It is going to be a big factor of it. And the benchmark paradox is, if your product's chances of winning a benchmark are 50-50, because people don't know how to run benchmarking, you'll usually lose. And I've seen this so much, and I had a sales guy say, explaining to him that people don't know how to benchmark, and they're going to mess it up all the time. But he was happy. It's like, that's okay, because if it's a coin toss, I'll win half the benchmarks. It's like, well, but that doesn't happen. You're not winning half the benchmarks. You're winning 10% of the benchmarks. You should be winning 90% of the benchmarks. And the problem is, if a company wants to switch products, let's say we want to switch to FreeBSD, we're not going to run one benchmark and base it on that. We're going to run 3 or 4 or 5. And to be really sure, you need to win them all. And so now it becomes probability. If you're doing a coin toss and you have to win all of 3 benchmarks, the possibility of throwing heads 3 times is now about 12.5%. And that's what actually happens. So how do we solve it? Fortunately, I do have a way. One thing I can say about fixing the huge problem of benchmarks, so to finish this section on a higher note, for any given benchmark result, simply ask, why isn't it 10x? A big problem with benchmark results is we have no intuition about what they mean. So if as I drove here this morning, if my speedo said I was doing 1,000 miles an hour down the highway, I would know something was really wrong. It's like, after the conference, I need to go get my car checked, because obviously this is bogus. People don't have that intuition with benchmark results. And so I'm sent these just crazy, I have often, not often, but more than a dozen times been sent a benchmark where the network throughput is greater than the network interface's maximum speed. So you've sent me a 16 gigabit per second benchmark over a 10 gigabit interface. It's like, how do you do that? That doesn't work. People don't have, you're not born with an intuition for benchmarks. So you don't know whether they're bogus, but ask the question, why isn't it 10x? So I've done 1,000 requests per second. Why isn't it 10,000? Answer that question. And the process of answering the question will unveil a lot of the mistakes you've made. And that's active benchmarking. So with active benchmarking, it's a methodology that I've been documenting. It's pretty simple. It is root cause performance analysis while the benchmark is still running. And so when people ask me to look at benchmarks, I say, can the benchmark run 24/7? Like, set the duration to be a week and just leave it running, because I'm going to log into the system while it's running and then do root cause analysis as though I was root cause analyzing an application. And during that process, I will uncover all of these mistakes. And I'll answer the question, why isn't it 10x? So it takes time, but it uncovers most mistakes. What most people do is what I call passive benchmarking, which is where you run the benchmark, you hit enter, and then you go and get a coffee and wait until it's done. And then you get the results, and the results, you have faith in the results. You don't actually analyze what it's doing while it's running. So active benchmarking. It takes time, but that is, if there's just one thing I can get you to do accurate benchmarking, it's that. So the second last topic is profiling. Really important for performance analysis. Now here's a great quote that I'd like you to read, and then I'll ask how many people in the room think they can do this themselves. So just spend 30 seconds reading this. So it's saying, as an experiment to investigate some performance, blah, 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 the CPU is saturated, but it has 30% of it. The time in the system is 20% is Ethernet, IP packet processing is 10%, TCP processing is 30%, checksum in 25%, and user system call handling is 15%. So a breakdown of kernel time. Hands up if you think you could do this. If I gave you a system, you could give me those numbers. So I've got one person, two people, good. Thinking about it. I can do it now because I'll use pmcstat or DTrace and I'll do flame graphs. You know, I'll get the job done, like using very, very modern tools. This quote is from Bill Joy in 1981. And he's doing analysis of the TCP IP implementation he was working on. And that is an example of, but this is great because it's also an example of active benchmarking, where he's analyzed what's going on and is giving you this breakdown. It's fantastic. I'd love to know how he did this, what tools he used back in 1981. Yes? Gprof. So you could Gprof the kernel? Yeah. Okay, cool. Gprof, great.
Heavyweight because I can Gprof. It carries about a 9 to 12% overhead. Okay, I don't see that.
So these days we have lots of modern tools, and this is something you can do. But this is a great example of what you want to do, breaking down a performance benchmark into the limiting factors. So profiling tools on FreeBSD, PMCstat and DTrace. PMCstat counts PMC events, performance monitoring counters, and you can record samples of kernel user stacks. Like let's do a kernel stack every 64,000 level 2 cache misses. FreeBSD actually has great PMC docs, documentation. So like the man pages, pmc.sandybridge and so on, which explain what the counters do. Profiling, just so you can see what PMCstat looks like, I can say system stacks, resource stalls.any, output to a PMC log file format, and for 10 seconds is my dummy command. And then I'm going to read it and emit it as, in this case, a call chain, which looks like this. I can also emit it as a gprof output or a kcache grind output, and then read that in other tools. And of course, instead of resource stalls, I can say all sorts of other things. If you do PMC control -L, there's lots and lots of counters, more than that would fit. Some of them are high frequency, so you do want to throw in a -n, which limits how many counter events per sample. I was messing around to try and come up with a way to show you the counters that exist, And so I was trying Unix with tables and things. So you can see like there's, on this system, and I'm running it on Intel Sandy Bridge, there's 37 counters for the level 2 area, level 2 cache, 31 for branch prediction, 22 mem, 15 for micro ops, and so on. But also came up with a picture. So here's a very simplistic picture of a CPU that I came up with. Most of this is probably pretty obvious. I've also got the instruction decoder, load and store buffers, and there's other buffers, branch prediction unit, micro op cache, which will get the decoded instructions, floating point unit. Everything else should be pretty obvious. And then decorated it with the resource groups I found on my Intel Sandy Bridge box. So this might actually help explain better than anything else I can do what pmcstat does. So pmcstat, you can look at the internals of your CPU and see what all of the components are doing. So I might want to look at my level 1 data cache access, level 2 hits and misses, last level cache, instructions, and so on. And really understand, like, if I'm on CPU and I'm doing CPU cycles, what are they spent on? That's pmcstat. DTrace profiling is, if you need to KLD load DTrace all, and DTrace can do a lot of things, but it can do profiling. So I can say, for example, profile kernel stacks for 60 seconds at 199 hertz, or profile user stacks at 99 hertz. I would slow down user stack profiling because it's more expensive when you're doing translation of the stacks. And just to see quickly how that looks, so I'm on a system with not much load right now. So let me just run a command so that we've at least seen what the output looks like. These systems do different things during the day, so I wasn't sure if I would catch it during the heavy load or not, and I seem to have caught it during idle. So I'm just profiling at 199 hertz, and there's lots and lots of stacks, and mostly it's idle. It's a bit boring. I was hoping it would be doing something else. I've caught some other stacks in places. How about okay, so just because I happened to catch it at a bad time when there's no load, let's at least do some file system stuff, like checking whether a path exists. And that's better. Now I'm in I'm doing name I vput x. So here you go, vop lookup apv. That's better. So doing something. Now when you do profiling, so this is DTrace, and what it's doing is these are stacks and counts, how many times that stack was seen. The output is going to be really verbose. You get tons and tons of this stuff per second. It got really bad to the point where I couldn't make sense of profiles very quickly. And I do these profiles all the time. And so what I did was I came up with a visualization for profiles. Let me... called flame graphs. And so what flame graphs do is it's really simple. This is actually a flame graph on FreeBSD, and it is taking profiles. So this will eat either DTrace or pmcstat. It will take profiles, and then on the y-axis you have stack depth, and the x-axis is not the passage of time, it is just the population. The x-axis is actually alphabetical, and the color is random, just so that I can see the difference between frames. I can mouse over it. So if I mouse over this, so here I'm in Service IQ, it will immediately tell me the percentages of samples that had that frame. So 53% I'm here. This is actually a flame graph from our OCR place. Oh, here I am in the file system, so vn read. I can click on it, and we'll do click to zoom now, which is a feature that was just added, which is really cool. So this tower here is, we're doing vn read I'll just click on it so you can see it. So VM read, FFS read, cluster read, and then the various components that are necessary for doing a cluster read. So, oh, what's this guy? Oh, this is buff strategy. And so here's the CPU cycles involved in creating a buffer to issue down to the disks. This is great for learning how the kernel works and as well as the great book that's just been published. So you can navigate around structures and not just see what's active, but also see how active it is, how often it's on CPU. And as a performance engineer, I like it as well because I just mouse over areas and it immediately gives me the percentage so that I can quantify speed up. So that's a flame graph. That's really cool. And one other flame graph I just wanted to show is the CPI flame graph, which I only just did this week and blogged about it on Friday. CPI flame, I've wanted to do this for a long time, but I didn't have flame graph differentials. So flame graphs for a long time, the colors are just random, so you can see just see if two towers are close to each other, they visually look different. But I can use color hue for something interesting. And so this is, again, it's an OCA, but what I'm now using pmcstat. The width of the frames shows how much I'm on CPU. The CPU, by the way, follows the top edge. So the CPU is actually running, that's the program counter on CPU. That's the ancestry of how we got there. So the wider functions that have a top edge of what's actually running directly on CPU, the guys beneath it are who's responsible. But what I've done is I've decorated this with why we're on CPU. So I've used pmcstat to measure cycles per instruction, and the bluer it is, the more stall cycles in that function when it was on CPU, and the redder it is, the fewer stall cycles. So now I can look at this area over here, that looks really interesting, and see that VM page alloc had more stall cycles than mutex lock sleep. Mutex lock sleep didn't have so many stall cycles, that was just burning instructions. Which, as it turns out, is really not surprising because VM page alloc is walking page structures, and that's going to do a lot of memory work. And mutex lock sleep is doing cycles. It's doing a spin loop. So in this case, it's actually not hugely surprising, and we already know about that, and we're already working on that. But this is useful for when you don't know, and so when there's going to be surprises in the code path, and it's like, oh, I didn't know, like, this part of, you can do this for applications as well. This part of my application is actually doing stall cycles, and that's why it's burning CPU. So, and I've wanted to do this for years, but I just couldn't get it to work on Solaris because of the providers. But on FreeBSD, PMCstat works, so it's the first time I got it to actually work doing a CPI flame graph. So I'm actually pretty happy.
What's white?
White is just, it's kind of, it's a color scale, and so white is right in the middle. I know it stands out a bit too much, but maybe I should try to color it gray. So that's flame graphs. You can run flame graphs for DTrace or PMCstat. I'll post the slides, and the code is on GitHub. And the last section to cover briefly is tracing. And for tracing tools, Trust, TCP-dump, ktrace, and DTrace. We have DTrace on the BSDs, which is awesome. Kernel and user level tracing is programmatic. I know we heard yesterday that the code needs a complete rewrite, but it's a good idea. That's fine. There are definitely, as with any body of software, there's things you can improve, but making it work faster in the kernel would be pretty interesting, and like user space as well. There are stable interface providers like IO, IP, lockstat, proc, shed, and so on, and unstable interface providers as well. So Pete gives us user-level dynamic tracing, FBT for function boundary tracing, and system call. And we should enhance and develop more on the BSDs. Learning DTrace on FreeBSD, I wrote a... So have you ever had a case where the software you write today, the version of the software of something you're writing, is always the best? And if someone says, oh, I'm running a version of your software from 2 years ago, I was like, oh man, that's awful, don't run that. That's like, I can't believe anyone's running that. You have to run my latest version of the software. And then in 2 years, that latest version, which is really awesome, that's now going to be the awful thing. So I've created a lot of DTrace stuff over the years, over 10 years. And so the new stuff I'm doing is now only on FreeBSD. And the new stuff is the awesome stuff. And that's the stuff I want you to use. Because if you look at my old stuff, like the DTrace toolkit and things like that, it's like, oh man, there's a lot of things I should improve. In fact, I wrote a blog post about all the mistakes I made in the DTrace toolkit. So the new stuff is the best stuff. And I wrote a tutorial for DTrace, learn DTrace in 12 easy steps. I've got a collection of one-liners. If you are going to get into this, there's a good book that will explain how the kernel works. I've got my copy. I should get it signed. And just to explain how DTrace practically gets used, and this is something that many at Sun got wrong. They had the notion that everyone would write DTrace scripts. But practically, you only need one person or a team at your company who can write them or write one-liners, and everyone asks them for help. And that's a more practical way to get a company making use of it. There are some exceptions. So you may work at a shop where everyone's going to be using DTrace, and that's fine.
Hey, Brendan, sorry to interrupt you. I can remove your machine and get you working again. Want me to do that?
How long does the reboot take? Because I've got like 5 minutes.
It takes 10.
It takes 12 minutes?
A couple minutes.
Yeah, you go ahead. All right. Thanks. Oh, that's right, because the next session's at 11. Okay, so DTrace one-liners, these are all on the FreeBSD wiki. And I tested them all on FreeBSD, so they work, they're really cool. I've created lots and lots of scripts in the past. So this is the DTrace toolkit scripts. And with the DTrace toolkit, I was doing performance consulting in APAC, and I had a whole heap of issues that I couldn't solve with the existing Solaris tools. When DTrace came along, I went and solved them. And that was really cool. And the DTrace toolkit became, because everyone kept asking me for my scripts rather than writing DTrace scripts themselves. So it just became a thing I shared. One of the biggest problems with the DTrace toolkit was it was gappy. It was based on the issues I was working on at the time, and there were some areas that should have had coverage that didn't. And so I didn't do socket stuff, and that's just lame. I should have done socket stuff. I hadn't been working in that area. I think it's pretty cool, and it has served a good purpose of helping people learn and understand DTrace. It's all open source. I then wrote the DTrace book with Jim Marrow, and I tried to, one of my primary objectives was to make sure I gave every area coverage, good coverage. And so I did the socket stuff and file system stuff and everything, went up and down the stack. The primary operating system was Solaris. There is some FreeBSD in the DTrace book. The biggest problem about DTrace is knowing what to do with it. Like, it's awesome, you can analyze all of these things. Go, what do I actually do? The DTrace book is over 1,000 pages, and one of the great things it serves is helping you see what you can do with it. And so you can use it as a pamphlet and say, this is what I want. I want to do the Q latency down in the block device interface. I want that script to work on FreeBSD, and then you just port that script. So you can use either, like, all the scripts I put in the DTrace book are also online on dtracebook.com. So you can use a lot of the scripts that I've created in the past just as suggestions of this might be useful, and porting the scripts to FreeBSD. Some of them just work because they're using stable providers. Others will take a little bit of work. Another diagram I drew once of some of the scripts I wrote for Solaris looks like this. I've written too many scripts. Way too many scripts. But good coverage. So I'm now writing new scripts, and my new stuff is the best. And I just drew this slide. So I have some FreeBSD scripts. I've been trying to figure out where to publish them, and leaving it to the last minute. I didn't know where to publish them. So I actually stuck them on GitHub this morning, so that at least they are open source on DTrace-Tools. But they'll probably go somewhere more meaningful, like on the FreeBSD wiki or something like that.
Just so you know, on FreeBSD, there's user-shared DTrace where we have a lot of scripts. So
yes.
Talk to me and we'll...
Yes, I realize this is the wrong place. It should not be on my GitHub. It should be somewhere else. So I'm now creating new scripts on FreeBSD, and this includes things like there's a much better, if you're interested in the iostat, you should look at the diagram in the FreeBSD implementation book. It's much better than this. Go up and down the stack, looking at like MPS latency, XBT latency, bio latency, doing file latency checks, socket scripts, accept to close latency, receive to send latency. Let's go to the scheduler. Run queue latency off CPU slower. So when we're timing how long something was off CPU from the scheduler. You can go into TCP. So when you drop packets, let's do information about that and print it out. Net ISRS. So let's look at some of these and see if my boxes come back. But I also have the script sitting around. Actually, I have the script sitting around because I just published them on GitHub. So like, this is what I did this morning. All right, here we go. So let me just make this bigger. Just to give you an idea of what the scripts look like. Yeah, this is a really simple script. FBT is the function boundary tracing provider, and that lets us trace kernel function entries and returns. Trace this function name, net ISIQ, trace the return of it. arg1 is going to be the return value. arg0 is the program counter offset. And then just print out stuff. If I'm arg1, if the return value of net SIQ is not 0, that's interesting, right? So how many people use cscope? Lots of people. What was I tracing here? Net SIQ. So okay, so like, oh no, this is terrible. Net SIQ source. Okay, so you can see like this function returns error. And I wrote this script because I was debugging errors and I needed to know if we were having Q errors. And so pretty simple to come up with an arbitrary script that did just that. Other examples include, here's my TCP drop script. This one's a little bit advanced, but that's okay. So if we're going into TCP drop, kernel function, then take arg0, which is going to be a struct TCP CB, and PCB, and then translate it and print out local and return addresses, just so I can dig out information on retransmits. And disk scripts include MPS latency. Oh, that's a nice script. So MPS in queue request, timestamp indexed on arg1 on entry. So that must be a good function to look at. Okay, so arg1 is the MPS command, and I'm using that as a unique identifier to store a timestamp. And then on return, when you complete that I/O, if the timestamp was sent to a histogram or quantize. Let's see if our system's up so I can actually run some of these. Alrighty. Because I don't have the... Okay, apart from cscope, how many people use UU encode every day? And PB copy. How else do you move things around? Like, I don't want to SSH this thing around. So while that's running and gathering information, so just UU encode, PB copy on Mac OS X just throws it into the paste buffer, then I can UU decode it, and it preserves my tabs. So, okay, so now I'm doing things like look at the MPS latency as a histogram, and I can see 500 requests had about 1 millisecond, 1 to 2 millisecond latency, and then there's a gap, and then there's 8 to 16. So really interesting. You see this stuff all the time. So bimodal latency, 2 different modes, and then I will start using scripts to analyze it in detail, find out why we've got 2 modes, and look at the maybe event by event to see if there's a pattern between them. See if this is the result of queuing and that's the result of not queuing.
Oh, sure, it's a 7200 RQ.
7200. Yeah. This is actually going to be a slower disk, so you're going to have.
So 8 milliseconds is the seek time for and read.
Yeah, so this looks like the seek time for random read. But why is that so big? Why Why 1 millisecond for the slowest read for a disk? That's really slow. Did I do a disk? Okay, I'll add this script and I'll add it to GitHub. Well, it's been a while since I've written this. So let's do. That should be. You didn't call it something else. Yeah, 3 columns. B count is in buff info. This is going to be why struct BIO. You are a member of struct BIO. I know you are. Okay, fine. Yeah, I should have written this script beforehand. B count is not. Is B count? What's that? I can just use B underscore length. All right. Is it len or length? Nope. B count. Ah, thanks. Yeah. It doesn't look like that's the right struct. Okay, so what I would guess this would be, obviously I'd need to write this thing beforehand. What I would guess that latency would be is we're actually doing large reads, and so they're probably 1 megabyte I/O, and that's why the minimum is so large. That's probably tiny I/O. That's probably large I/O. I just need to dig out the size. The most important thing about DTrace is not how to write those scripts yourself. It's that you can do it. So the most important thing is if you need to answer these sort of questions, that it's possible. And maybe I've already done it in my FreeBSD scripts or someone else has. Maybe you can ask someone to do it. Or maybe you are the person who's going to write that script. But that's the most important thing of all. So last thing to mention is when I'm doing a lot of this analysis, so if I'm analyzing latency of, say, kernel functions or disk I/O or queue latency, heat maps are a great visualization to show that. And that's where, over time, you can see bimodal distributions and how things change. And so heat maps might be the killer app that encourages people that they actually need things like DTrace to get rich data out of the system. So, and that's my talk. 5 topics, very quickly: observability, methodology, benchmarking, profiling, and tracing. And I'll post the slides online.